get started now with our next speaker. It's Dr. Mathias Vuille, who is a professor of atmospheric and environmental sciences at the University of Albany, State University of New York. His main research interest is climate variability and change in tropical South America and East Africa, as well as tropical glacier-climate interactions and tropical paleoclimatology. And his work has helped me a lot personally because I work in East Africa, and so his interpretation of isotopes and how interactive variability influences them has been really beneficial. So with that, you can take it away.
Great, thank you so much. I first really want to thank S4 for organizing this. It's been such a pleasure so far, and I'm looking forward to the second half of this meeting in the field as well. And I also want to thank just the local team here on the ground from Brazil. I've been coming here for many, many years. You're probably sick and tired of me, but every time I'm here, it's just such a wonderful experience and welcoming atmosphere. So what I'm going to talk about is work that we've been doing within this Pire Create project. Some of it also dates back a little bit before that. But it's really collaborative, interactive work. There's a lot of people involved in this. Too many to put on the slides, but many of them are here in the audience. You know who you are. But it's work between the institution here at USP. In the US, we're two groups. One is at UAlbany, where I am. The other one is at Columbia University. And we also have a project team in Argentina at Yanigla. There they do more trivial research, so I won't be talking about today. So Marcella, I think it was, asked me to talk about speleothems and climate models. I'm happy to do that, but I also, right off the bat, have to make a disclaimer here. I'm not a climate modeler, okay? Most people in my research group, my graduate students, my postdocs, they use climate models in their research. Some also run their own climate models. But most of the time, we're using models that already exist, that are publicly available. Or sometimes we team up with actual modeling groups who do that kind of work. I'll show a few examples of that in just a minute. The other thing I just also quickly wanted to show you, if you're interested in working with climate models and speleothems, there's a wealth of information and literature out there, that a lot of really good papers. Delve into it, read them. What I'm going to talk about is very narrowly focused on our own work here, mostly in South America, so I'm not going to give you a full picture or a global perspective, but there's a lot more here. You probably can't read it, it's too small, but Kira Refeld's name is all over this, as are some others that are here in the room today. So, I don't know, how many of you actually work with a climate model or are planning to work with a climate model? Oh, there are quite a few, good. So, but maybe for some of you, it is somewhat new, so I want to first give a little bit of an introduction, so some basic aspects of what a climate model is, what we can use it for, but also what maybe some of the limitations and drawbacks are. One of the nice things about a climate model is you can visualize it, right? And I'll show you some examples of that as we go through the talk. So you can think of it as a kind of a virtual world of our physical environment that we're trying to model and simulate. If you're actually a coder, a programmer, you may think of this in very different ways, just as a string of code. This can come in many different forms. The first time I sat in front of a computer, I was in middle school. I used these things here at the bottom, punch cards. Looking back, it seems more like I used a typewriter rather than a computer, but in essence, it was an early version of it. But fundamentally, we're trying to represent everything that is happening here outside somehow in a mathematical and physical form, trying to represent that. So, because of that, we have to make a lot of assumptions. We have to limit ourselves in many ways. First of all, everything that is happening here outside, we cannot possibly put that in a climate model. We can't describe all that. If you think of all the processes that occur on so many different time scales, on so many different spatial scales, in the atmosphere, in the biosphere, hydrosphere, cryosphere, also the lithosphere, of course. We can't do that. So we have to pick and choose, okay? We have to say, well, what are the first order most important things that we need to have in our climate model, and the rest we will neglect. Also, even the things that we want to include some of those things we don't really understand that well. So we have to find a way to try to represent it in the climate model. We would like to do that all in terms of physical equations, but sometimes we can't do that. We have to use sort of semi-empirical relationships. We have to idealize a little bit. And finally, the climate model is kind of a closed system. You have to tell the model everything that happens from the outside. But if you think, for example, so we use climate models now a lot to project what might happen in the future, right? That's the one tool we use. And you can see and look at all these emission scenarios. But what happens if in 2 years we have a massive volcanic eruption? It would throw our climate into turmoil, but we don't, and we're due for one actually, just on a side note. But we can't put that in a climate model because we don't know when it would happen. We can do it for the past, or we can make it as a hypothetical case, but not trying to simulate reality. So, in that sense, we have to be honest and say, you know, models are models. They're not reality. That is really important, and some modelers, even some of my colleagues, sometimes tend to forget that a little bit. That is not to criticize models at all. Models are really, really useful and helpful, and I hope that I can show you that a little bit in my talk. But they are not reality, okay? And in particular, models, for most of us in the climate community, are really useful because we want to know, we're concerned about climate change, what will happen in 50, 100 years? What is our world going to look like? The only real tool we have available for that are models. If I could, I would much rather put an instrument outside and measure what the climate will be like in 30 years. But I can't do that, right? Observations of the future, currently those are not available, right? So we have to stick to models. So, why do we need models and why do we need paleoclimate models? One thing that is really nice about climate models is that they're physically and dynamically consistent in the sense that we can look at different variables and the way they interact with one another is consistent, at least if it's a good model. So we can learn a lot about the climate system, and we can learn how sensitive the climate system might be to specific forcings. We can also set up a hypothesis of what we think happened in the past, and we can try to falsify that using a climate model. So maybe we can learn something about why the climate changed in the past in a specific way. Also, when you use observations or proxy data, you usually get information at one specific location. Climate models will give you a spatially complete picture everywhere, right? And over the entire time period that you run your model, there's no gaps. So models can inform paleoclimate, but it also goes the other way, right? If you have a good climate model, you should be able to more or less simulate what actually happened in the past, and we can use the proxy data to basically validate that, right? We can see, well, can the model reproduce what the observations tell us that really happened? So it's a two-way street, really. But specifically for the speleothem research, many of you work here with speleothems, and they're great, and they tell you a lot about how the climate varied in the past, but oftentimes they will not tell you why, only how. If you combine the speleothem research with climate modeling, then maybe you can also answer the why question. Not always, but sometimes it might work. Okay, so if you run a climate model just like that, it's not going to know what you want to do. You need to tell the model a few things first. Okay, and we refer to these as forcings. Depending on the time period, you may have to implement that or not. So obviously, you need to tell the model if you're looking at a time period where solar irradiance varies. Longer time periods, you need to tell the model what the orbital forcing looks like. If you want to look at the last 1,000 years, volcanic forcing is the most important external forcing we have over that time period. You need to tell the model when these eruptions occurred. But then we also have internal interactions, and now it depends a bit on what model you use. If you have a full-blown coupled Earth system model, it will do that on its own, internal variability. The ocean and the atmosphere, for example, they will communicate with one another. it will create its own ENSO variability. Not at the right time, as we have them in observations, but it will do it. And if it's a good model, the characteristics will be quite similar. Older models, but they're still in use today because they're useful for some applications, so-called atmosphere-only models. They do not have an interactive ocean, so they do not create ENSO events. You actually need to prescribe the sea surface temperature, and you need to tell the model what it feels at the bottom of the atmosphere, what the ocean actually does. Okay? So it depends a bit on the model that you're using. All of these are natural forcings. But of course, since the start of the Industrial Revolution, if you want to simulate that time period, we also now need to include greenhouse gases and aerosol forcing, which both are really important. And depending on the time period, again, maybe also land use change. This, again, to some extent, depends on the type of model. If you, for example, have a model with interactive vegetation, it may simulate forest dieback or such things on its own, or it may not do that. Fundamentally, you have sort of two types of different models. You can run a model just over a long period of time and see how it evolves. These are transient simulations. Or you can just pick out a specific time period in the past and set the boundary conditions to that time period. Then we're talking about snapshot or time slice experiments. And those are especially useful deep into the past because it doesn't make a lot of sense of simulate 1,000 years of variations over a period in the past where we don't really know much about how the forcing varied. So certainly early work and still used by PMID4, for example, for the last glacial maximum in the mid-Holocene. We oftentimes just look at these so-called time slice simulations. Now, climate models come in all different shapes and forms. I'm not going to go through all of these, but I just wanted to show you. Not for every question that you want to answer, you need to use the most complex model, because it'll become computationally very expensive, takes a long time to run. If you just want to simulate the energy balance of a melting snow surface, you don't need an Earth system model. You can do that in a one-column model where you just calculate the radiative balance, short and long wave radiation, latent sensible heat flux. That's it. You don't need all of these other bells and whistles. Okay. This may not mean much for you. Maybe in a visual way it's a bit easier to think about this. But most of us, when we talk about climate models, we probably think about something like this, where you divide the Earth up into a number of grid cells at the surface, but of course also vertically in the atmosphere. You have many different layers. What's not shown here, you also do this in the other direction. You have different soil layers, for example, of course many different layers in the ocean and so forth. Now, because of this and all these assumptions that I've gone through, there are some limitations to climate models. Grid resolution is one. We would like to have very high resolution models, but the more you increase the resolution, the more sluggish your model will become, the longer it will take to run, and it's expensive. As I mentioned, a lot of things are happening outside that we don't understand, or maybe the processes are so small that they are too small to resolve in a grid cell. Then we resort to what we call these parameterizations. So we basically use semi-empirical equations to describe that process as best we can. You also, if you run a simulation over a long period of time, you will start to increase the model noise as you move forward one time step to the next through truncation. ECC report that shows you a little bit how the model complexity has increased over time. So what's shown here is the number of models that participate in this so-called CMIP. So that's the Coupled Model Intercomparison Project. The idea behind this is that all modeling groups around the world are given a set of experiment simulations that they should all run in the same way, using the same forcings, the same boundary conditions, so we can compare the models among each other. And these are different model generations. So CMIP 3, that's from around 2007, CMIP 5, 2013, and CMIP 6 is now the latest model generation, so 2021 from the 6th assessment report. And you can just see different things that have been added over time, right? So CMIP 3 in 2007, very few models included atmospheric chemistry, a carbon cycle over land, interactive vegetation. But now more and more of these modeling groups are adding these things, making the models more realistic. Now, if we want to start to compare models with observations or with speleothems, we run into some problems. One is a scale mismatch, and the other thing is also a variable mismatch. Scale mismatch has a lot to do with, you all know more about speleothems than me, but when you sample a speleothem and you take a few milligrams of calcite powder for each sample, and that's what your record then basically represents. And the smallest grid cell of a fairly high resolution global model today maybe has 100 kilometer size. So it covers an area of 10,000 square kilometers. Be aware of that. Because sometimes, we want to zoom in and, well, what does the model do right where my location is? But you're not supposed to look at the model like this. You're supposed to look at it like this, big picture, okay? Also, so these are the discrete spots. The temporal dimension is another thing. So you may have, if you're lucky, a speleothem that covers a very, very long time period. You're probably not going to be able to simulate a transient simulation over this entire time period, at least not with a full-blown Earth system model. Maybe with a model of intermediate complexity, you can do it. So what you will resort to then instead is you pick out certain time periods that particularly interest you. The mid-Holocene, or the last glacial maximum, for example. And finally, models usually don't give you the variable that you're measuring in your speleothem. If you're working with trace elements, the model is not going to spit out the strontium-calcium ratio for you. Right? So you're going to have to take something from the model that you think your proxy is sensitive to and somehow link them up. And I'll talk a little bit more about that in just a little bit. So one thing you can try to do is, sort of mediate that scale mismatch by upscaling or downscaling. So for example, you can run a model just over a certain region at much higher resolution. So-called regional climate models. Or you can add an intermediate model in between the climate model and your proxy, so-called proxy system models or forward models that take the output from the model as an input and then try to sort of simulate the processes that actually lead to the formation of what you're measuring in your speleothem. And an example of that, of course, are isotope-enabled models. I'll give you a little bit more information on that as well and show you some examples. But trying to convert what you get as output in your climate model into something that is more related to what you measure in the lab is important and I think really helpful. So the isotope-enabled climate models, a lot of people use this now. Most modeling groups now have at least some of their simulations done where they include an isotope component. And we already have the full hydrologic cycle in the climate model anyway. So now we're just adding the isotopes, but we already have all the fractionating processes, right? All the changes of phase from liquid to solid to gas, the mixing and so forth. So here's just an example. This is from a recent review paper by Sylvia D. You can think of this as an air mass moving from warmer to colder environments, from a tropical to a high latitude, and we have this Rayleigh distillation, this progressive rainout, the heavier isotopes condensating first, leaving the remaining water vapor increasingly more depleted of the isotopes. So the climate model will give you as output then oxygen 18, in the precipitation. You can also look at it in the vapor phase, for example, in the atmospheric water vapor. It doesn't solve the grit issue though, and it's still not the same. You might get oxygen 18 in water, but that's not necessarily the same as the oxygen 18 in the calcite that you're measuring in your speleothem, right? So there's still an additional step there. So that's sort of the theory, the background behind this. Now I'm going to show you a few applications. You're probably sick of this figure. You've probably seen it at least 3 times already, but I'll show it to you one more time because I really like it. This is from Chico's work. We were working together at UMass, as he mentioned on Monday morning at the time. He did this, and I did this, and then we realized, hey, this kind of fits quite nicely. So just as a reminder, if you're not familiar with this paper, this is a record from northeastern Brazil, a speleothem or multiple speleothems. And you can see here the most negative values during the mid-Holocene. And at first glance, this seems to fit really nicely with the insolation curve. But if you look at this here, you will see that it's the exact opposite of what you would expect. You have the most negative values at a time of an austral summer insolation minimum. It's not what you would expect in a monsoon environment, right? But this record is not in the monsoon environment, it's adjacent to it. And whenever you have strong convection in a monsoon region, you have a lot of updrafts, a lot of uplift. Air is moved into the middle and upper troposphere. Well, that air is going to have to come down again somewhere. So when you have strong monsoon convection, it is balanced by subsidence in adjacent regions, and in particular over the subtropical oceans. In fact, the reason we have high pressure systems over the subtropical oceans is because of monsoon convection. Okay. And if you look at a map, northeastern Brazil is kind of like a knee. It kind of sticks out there into the subtropical area. And so this region here is strongly influenced by subsidence. So when you have a strong monsoon, you also have strong subsidence over northeastern Brazil. And that's what really explains this. And it's shown here in this model analysis. And again, I mentioned in the beginning, I'm not a modeler. This is actually the actual model simulation here was run by Martin Werner, who was at the Max Planck Institute in Jena at the time. We worked with him quite a bit. But it's a very simple model. This is an atmosphere-only model for the mid-Holocene. And you can see here this precipitation dipole with enhanced precipitation during this time over northeastern Brazil, where the rest of tropical South America sees reduced precipitation. This is expressed also as a dipole in the oxygen 18. And you can look at it then in different dynamical variables that are physically consistent with this because they're from the same model simulation. So omega 500, that is upward, downward, vertical motion in the mid-troposphere. In the tropics, precipitation is not driven like in mid and high latitudes, mainly by advective processes, but by convection. So the upward-downward movement is actually more important than the east-west or north-south movement. And over here you have also in the lower atmosphere a velocity potential and divergent wind. It's an approximation of the actual divergence that occurs at low level. If you have divergence at low level, that air also needs to go somewhere. It can only go up. It's also an indication that you have enhanced convection. So that was a very early, simple application. Now people are moving more and more to these longer transient, fully coupled isotope-enabled models. Is in particular these so-called iTrace simulations. So these are runs that now are transient from the last glacial maximum through the deglaciation, isotope-enabled. They're based off the Community Earth System model. And here again is an application of that over South America. This is still work in progress. But an analysis done by a former postdoc of mine, Ernesto Tejedor. And we're looking here at the difference between 16K, so 16,000 years before present, compared to the rest of the Heinrich 1 event. And the colors here, it's a bit hard to see, but the brown colors are more positive oxygen 18 values and green more negative. So this is from the model, and then you have all these dots here. All these dots are places where we have isotopic records from that time period. Some of these are not published yet, and not all of them are speleothems. We can also use ice cores for that analysis, for example. They're also shown here. But you can see we have a very, very nice match. This really just projects right on top of the model. And when you have such a nice match, then you can say, okay, it seems this model works. So now we can again try to investigate a little bit more what's actually happening here. I don't have time to go into the details here, but again, the meridional and zonal overturning circulation are fundamentally important in that region. And it shows that during this time period, both, if you want, the regional Walker and Hadley circulation were perturbed. And that's how we can explain both the precipitation, which I'm not showing here, and the isotopic signal at the surface. Now, so far what I've shown you, we've tried to mimic what we actually observe in the real world. But sometimes that's not the best use of a model. Sometimes you can actually learn more when you do what we call sensitivity experiments or so-called single forcings. So we're just interested in knowing what happens if we only allow one specific forcing to vary. And for the last 1,000 years, the most important one is volcanic forcing. When you have strong volcanic eruptions, you have sulfur gases ejected into the stratosphere, where liquid sulfate aerosols form these scatter sunlight in all directions. But the end result is that you have less solar radiation at the surface. So our planet is cooling for a few years following the volcanic eruption. Because these aerosols don't stay in the atmosphere very long, they are not well mixed in our atmosphere. It's not like greenhouse gases. So it really matters where these aerosols are located. And that depends on where the eruption occurred. It also depends on the prevailing circulation at the time. And it depends also, to some extent, at the season of the year when this eruption occurred. But we have eruptions over the last 1,000 years where most of these aerosols were in the northern hemisphere. We also have some where they were mainly in the southern hemisphere. The reason this is important is that the hemisphere where you have more aerosols will cool more. So you will get a hemispheric asymmetry in the cooling, so you change the hemispheric temperature gradient. And precipitation in the tropics in particular, and that's what's shown here in the colors, is very sensitive to that. The tropical rainfall belt will move away from the colder hemisphere towards the warmer hemisphere. So what is shown here is a composite of the, I believe it was 16 strongest eruptions, or all the eruptions stronger than Pinatubo that occurred over the last 1,000 years. And we are now looking at the precipitation response in a climate model when the aerosols resided primarily in the northern and the southern hemisphere. And you can see you get almost the inverse signal. Here at the bottom, it's just the difference between the two. Right? So if you have a speleothem and you think it's really, really high resolution, it is so excellently dated, so precise, I can pinpoint individual eruptions, and I'm looking at Nicholas because it's something that we've been talking about a lot. Then you may be able to use something like this, but you would still have to know where the aerosols resides for your particular eruption. I should say all this work was done by a former PhD student of mine, Chris Colosi. And again, it was done in collaboration with a modeling group. The actual model results here were done by Allegro Legrandi at NASA GIS. So here's the same thing, but now we're actually not looking at precipitation. Now we're looking at the oxygen 18 response because it was an isotope-enabling model. And again, I'm just biased towards South America, but if you look at the response here in DJF, that's the monsoon season, you get quite different results depending on where the aerosols reside. Okay. So you cannot just take a speleothem and think the signal to volcanic forcing will always be the same. It likely will not be. At least not according to these model results. Another possibility, if you want to just use off-the-shelf models, that is fairly easy to do, you can go to the PMIP data archive. So PMIP is similar to CMIP. The only difference is it's the paleoclimate model intercomparison project. But again, it's tied to CMIP, and the idea is different modeling groups running the exact same paleoclimate simulations The big advantage of this is now you can use multiple models, you can reduce the model dependency of your results, because you can create an average across a range of different models if you want to. PMIP also has certain time periods that they favor. Initially it was, again, the last glacial maximum, the mid-Holocene, and the last 1,000 years. But they have now also expanded a little further back in time, including the last interglacial and the mid-Pliocene. Another alternative you have is if you work with one speleothem in a particular location, that's great, do that work, but then take a step back and think about where are there other records, other people who have done the same thing, and maybe I can do some kind of joint network analysis from many different sites. This is an example from South America, again in collaboration with all our colleagues here in Brazil. Rebecca Orison, a PhD student of mine, did this. And you can see everywhere where you have a symbol here in orange, we have a paleoclimate record. This is for the last millennium. Again, most of them are speleothems, but we also used an ice core record and also a highly resolved lake record using lake calcite oxygen 18. The big advantage of doing this type of work, so what Rebecca did here is she performed a Monte Carlo EUF analysis. It's a multivariate statistical technique where you try to extract the signal, the variance that all these records have in common. If you just have a record from one site, you will have a climate signal in there, but you almost certainly also will have a signal of the local environmental conditions that are unique to your site, that an adjacent site somewhere else will not have, or it will be different. That may have a lot of really important information, but from a large-scale climate dynamics perspective, it's climate, people would say that is noise. Okay, that's not what we want. We want the big picture signal that all of us have in common. And this type of analysis allows you to extract that type of information. And you get a result that then looks something like this. So this is the first EOF. Again, wherever you have a dot, you have an actual record. All the dots that have the same colors, they basically vary in phase. Where you have the other color, it means that they vary out of phase. It still leaves you to understand what this actually means from a physical perspective. Here in South America, because these are records from the monsoon region that's sampled primarily during the monsoon rainfall season, they really, we believe, are recording this dipole. And we can see this dipole also seasonally. What is shown here in these arrows, so-called stream function, is the upper level circulation. And we have two really dominant features here. One is this anticyclone, this is the Bolivian high. And then we have a cyclonic circulation here, the Nordeste lobe. And it's this seesaw that we're recording in the isotopes. So the isotopes really are the surface expression of the large-scale circulation. And that's what we can extract because all of these records feel that in one shape or another. How this varies over time is basically expressed by this time series down here, the so-called time expansion coefficient or principal component analysis. Okay. The size of these dots basically indicates how strongly each one of these records correlates with this time series. And you can see Marcella's record here smack in the middle. It has the dominant signal. But you can see we have sort of two time periods here that are shaded in orange and blue, where we see kind of departures from the mean state. This is the medieval climate anomaly, if you will, and this is more a time period that covers the Little Ice Age. So we can now do a model data comparison where we just plot up both the model and the data results for those two time periods. So you have the medieval climate anomaly here on top, the Little Ice Age at the bottom. Again, I should add, I forgot to mention this. So this is from an ensemble of several simulations from the isotope-enabled community Earth system model. These are all model simulations that are publicly available that any of you can use if you want to do so. But you can see that overall we get a fairly good match. There are some anomalies, which I think we know why. One of them is here during the medieval climate anomaly. But certainly during the Little Ice Age, this projects onto the observed data quite well. However, if you look carefully over here, you will see that we plot two different scales here. One is for the proxy data and one is for the model. And you can see why the spatial representation is quite good. The amplitude the model gets wrong. Okay? Something's missing here in the model. It produces a result that is much weaker than what we see in the data. Okay, something else we can do is we can try to link proxy data with model by using these proxy system or forward models. The basic idea here is that you simulate the signal that we see in our environment. That's basically the output you get from the climate model to what you actually measure in the lab. Okay. So we have a sensor. So that can be a tree, it can be a lake, it can also be a speleothem. Then you have the archive. So if you're using trees, the archive is the tree ring. If it's a lake, your archive is the lake sediment. In the speleothem, it's probably the calcite. And then you have the actual observations, what you're actually measuring in the lab. So a dendrochronologist would measure ring density or ring width. A paleolimnologist maybe measures varf thickness, for example. You may measure oxygen 18 or a trace element ratio. There are lots of models that do this kind of work. Sylvia D. at Rice University is a specialist who's done a lot of work in this. In my group, we also developed the forward model, but for ice, that I'm not going to talk about here because that's not really the topic of this workshop. However, I will say, as far as I'm aware anyway, many of these models don't really simulate the full chain. So I think for speleothem forward models, many of them, they may simulate the oxygen 18 in the drip water. You can make some assumptions about mixing and residence time in the aquifer or the epikarst above, but it doesn't give you the actual oxygen 18 in the calcite. And then another way of trying to blend your proxy observations with models is to do an actual data assimilation. Data assimilation is what we do for weather forecasts. It's basically you have a model so that you have a physical system that is consistent and it's spatially complete, but you know the model is wrong, so you constantly add all the observations you have to nudge the model in the right direction. If you've ever used reanalysis data, for example, that's what that is. But we can also do that for the paleoclimate. And there, again, there's a number of products that exist. Last millennium reanalysis, for example, the FIDA, I'm going to show you this example in just a second. This is a product that was produced as part of the PIRE project by Nathan Steiger at Columbia University. As far as temperature is concerned, we now have these paleo reanalysis going all the way back to the last glacial maximum, published a couple of years ago. So the FIDA covers the last 2,000 years. Again, this is Nathan Steiger's work, but as part of the PIRE project, we're not just trying to do science and education, we also do outreach, and we want to visualize research so that it becomes a bit more attractive and easy to understand. So I'll see if I can quickly show you this. So we work also with a visualization team within PIRE that is at UAlbany, and they helped us to actually project this FIDA onto a globe. And this, you can access this if you're interested in it. If you go to pirecreate.com, there's a tab called Data Visualizations. We have a number of visualization tools there. This is one of them. You see this is interactive. You can zoom in, you can zoom out. And right now, what we're looking at here is the mean annual temperature for the year 1 Common Era. And again, this is a data assimilation. So it's based on a model, but there's thousands of proxy records that have been assimilated into this. You can run this through time, but you will see the changes are very, very minor. And that's because right now we're looking at absolute temperature. In climate science, we don't really work so much with absolute temperature. We use anomalies, departures from a mean. So we can say we want to look at anomalies instead. I would have to indicate a reference period here, and it will then plot for us the difference in a particular year compared to this reference period. And now you can see this changes much more from one year to the next. You can look at specific years. So, for example, you can focus here a little bit on Europe. And let's go to the year 1816. Anybody know why I went to that year? You're all, okay. The year without a summer, right? Starvation, famine, and you can see how cold it is here. I should also add, you can click on any location and you can download the data from that location. It will just give you a nice little CSV file. You get a time series for the last 2,000 years. However, that is very enticing and easy to do, but be careful. This is a data assimilation system. In some parts of the world, the northern hemisphere, this is very well constrained because we have a lot of data. If you go to the tropics or the southern hemisphere, and if you go back several hundred years, what you will download is essentially a model result because there's very little proxy data available for that. Okay. But you can play around with that on your own. Again, if you're interested, biocreate.com and you'll find it there. Okay, I'm sure you're hungry for lunch. I'm almost done. The last thing I wanted to show you, also work in progress. So what I showed you, the FIDA is great, but it doesn't have isotopes. So one of my postdocs, Shiqiang Liu, is now incorporating isotopes into such a data assimilation system. It's very much focused on South America again, because that's what we're really interested in. But it's the same idea. You just add an additional variable. You take just isotopic proxy records, ice cores, lake calcites, speleothems, and you add it, in this particular case, to the model ensemble of ICSM, the isotope-enabled version of the CSM model. I just want to show you very quickly some very, very basic results. I know Kira's group is also working on something similar. I think you're using a different assimilation approach, so it'll be interesting to compare results. But here you see the records from the monsoon region that we assimilated. And if you just take the records and correlate them over time with what the model produces, ICSM, you can see these correlations are very, very weak. If you do the same then, after you assimilate the data, much, much better result. As it should be, is maybe not really a surprise, but it at least validates that this makes sense. What we're after, this is the record that I showed you before from Rebecca Orison. I think until now, this is the best monsoon index we have, because it's the most complete one of the last 2,000 years. It's not the best at every location. At every location, the records that you produced are the best. But sort of integrating over the entire monsoon region, I think this is kind of our target. If we take the ICSM and we just plot up over the same region, what the model produces, these are three different ensemble members. The black gray line is the mean. You can see it shows nothing like that. Just a lot of variability, noise as I would call it, flickering, but no low frequency component whatsoever. It's missing. Now we're adding the proxy data to that, and now we're looking at the model proxy blend, the assimilation component, and you can see it's much, much better. So here I've plotted all of them. So again, the green is the target, that's our proxy index. The gray is what the model tells us, and the red is what we get after the data assimilation. And now the nice thing about this again is because this is embedded in a global model, we have all the dynamical fields that we can look at. This is the oxygen 18 anomalies now during the Little Ice Age. Just looking at the model, and here is what we get. You can see now the amplitude is much larger. I told you before this model has a problem with the amplitude. We can look at precipitation, just model and assimilated data. And we can look at tropospheric circulation. Again, this may not mean much to you, but I'll just put it up here because this here, this is the hallmark of a strong monsoon and of tropical convection. These two anticyclones straddling the equator, we call them a dumbbell pattern. It's typical for latent heat release and a wave response. You see the same in the Pacific during El Nino events. This to me, as a dynamicist, is telling me, okay, this worked. This is what you want to see during the strong monsoon. The model alone, you can see even the direction of the upper tropospheric winds is wrong. Okay. So we clearly have improved on this, and we can now start to work with this. So it's very much work in progress, but it's something that I'm quite excited about, and we'll keep working and plugging away on it. So again, thank you all for your attention. I hope I haven't gone too much over time so that we can all get to lunch on time. Thank you.
Thank you for the excellent presentation, and we'll take a couple extra minutes for questions because we started a little bit late. Yeah.
Mathias, really nice presentation. Just one question. The data that on this visualization machine that you just presented from Fire Creek, is it just for visualization, or is something that you would just compare to another proxy?
Yeah, no, this is data that has been used in a number of publications. We're actually also working with Nicolas in one of his papers that hopefully will be out very, very soon. We have used the FIDA to try to better understand trends that we're seeing in big open caves in Peruasu that are affected by evaporation. So no, this is not just visualization. This is useful, very good data. If you want to work with the data, don't go to the visualization tool and download it there. Go to the repository where the data is actually stored and get the full actual data set. What I showed you really is more sort of for, we use this for talks and to try to tell people what, a little bit about paleoclimate. Mm-hmm. It's not necessarily for scientific use. That's really just for show, if you will.
Okay.
You mentioned about volcanic eruption. Volcanic eruption is causing aerosol reflecting that some radiation. So it will be affect how far it will be affect the area of effector and the time of affecting, because last year there's one eruption in Sicily. It's around 500 kilometers from us, but not affected. Not the effect. Yeah. No Tunisia or other close country.
It's a good question. You really need large explosive eruptions that really inject a lot of sulfur into the stratosphere. So the last one that really had a sizable climate impact was in 1991, Pinatubo. Nothing since. That's why, but we know, and this is reconstructed from ice core records, from both Greenland and Antarctica. That's how we know roughly the size of past eruptions. We had much, much larger eruptions than that in the past, which had a bigger impact. But since 1991, there hasn't been anything that really had a sizable impact. But Pinatubo, right after the eruption, just if you look at the energy balance, the radiative forcing, that cut the greenhouse gas forcing in half. But these eruptions, they don't last very long. The direct radiative forcing lasts a year or two. But sometimes there are then feedbacks, and particularly oceanic feedbacks in the Pacific or the Atlantic, that can extend that. And that's an active area of research, because I didn't have time to show this, but we compared volcanic forcing results in models and data assimilation system, and they are not consistent. Data assimilation products show a much longer response that can last a decade or even more, while in the model after 2 years, the climate signal, at least as far as temperature is concerned, is gone.
So how do you tackle the problem between the climate change and the signal it's giving, right? What I mean is since you are using past data, a sort of data, now that data was a response to some of the climate signals, and you are giving the absolute temperature for it.
Well, we can always calculate what you get as an output from a model, of course, is absolute temperature, but you can always convert that if you're interested in a departure from a specific time period, right? We can calculate anomalies. The bigger problem is more that what the model gives you is not the variable that you're measuring in your proxy. So you have to know or make assumptions about the climate sensitivity of your proxy, right? What does it respond to? Is it precipitation? Is it temperature? Is it something else? That, I think, is the biggest problem. I'm not sure if that answered your question, but we can talk more offline afterwards too.
I think there's a question in the back.
I have just a brief question. I noticed when you showed ICSM, the simulation, after assimilating, the only, let's say, the only feature in the simulations that's standing out is the strong response to the Samanas eruption, 1258, and that is lost. So that I thought was really interesting because that's sort of like the only multi-decadal feature that stands out in the last millennium simulations. So how can you imagine a way how we could incorporate these kind of short timescale features that we know that the proxies probably don't get? That might be overestimated in a way also by the model simulations. But how could we incorporate that? What could be a way forward? Is this going to be better with, well, you assimilated isotope in that example, right?
Yeah.
I think if you go back to the slide, it's really obvious, but if you know what I mean, then...
No, I think I know what you mean. It's a good question.
Yeah, I think we saw it. Yeah, here we see it at like 12.
Right, and here it's gone.
And
Yeah.
here it's gone, and on the next slide you have both, and you see that that's where they really, where they really diverge.
Yeah. So in the model, because we can prescribe the volcanic forcing, we know when it occurred, we roughly know how strong it was. The models do a good job with that, the immediate response, right? But if you don't see that in your proxies, and we are assimilating isotopic records that do not, except for 2 or 3, they don't have annual resolution for one. And then, you know, if you don't have precise dating, you will lose, those signals we lose here, no question. What we could do in theory is, if we have 3-ring records, right, a proxy that is high resolution, precisely dated going that far back. In the FIDA, those things are incorporated here. We have not done that, at least not so far, because we're really just interested, we're just starting this. We want to understand the low frequency signal here and that change, but you're absolutely right. This is not the right assimilation of interannual variability in that sense.
Yeah,
I don't know if that answers your question.
Yeah, I was going for the philosophical angle, sort of like saying, what can we do to say, okay, here we should trust the model more than the data that we actually put in. But you're right in the sense that probably a multi-timescale perspective is what we need to capture.
In our simulation, there's 2 records that have annual resolution that go this far back. One is the Calcaya ice core. The other one is Laguna Pumacocha Lake calcite record from Peru. The others, Aldir, Nicolas, Chico, you correct me if I'm wrong, but the others are not annually resolved. Subdecadal, very good, and definitely sufficient for what we want to do here, but not to find specific responses to eruptions.
Any last questions? Seems like everyone wants to go to lunch. All right, well, let's thank our speaker one more time. So just 2 quick announcements. If you presented a poster yesterday and you would keep your poster, you should go grab that now because that'll be getting tossed very soon. And similar to yesterday with filing up for the lunch tickets, we're going to do that again over here. So just come up whenever you're ready.